Solution concentration. So we have some qualitative descriptions, which can be useful. There's dilute. Dilute means that it has small quantities of solute, and concentrated means it has relatively large quantities. These are relative. You could have a dilute solution of one thing that would be considered concentrated for a different solute. And then there are many quantitative measures, and we're going to look at a few of them. Here's a nice table showing you a whole bunch of them. There's molarity, which is amount of solute in moles divided by the volume of solution in liters. There's molality, which is the amount of solute in moles divided by the mass of the solvent in kilograms. There's mole fraction, we've looked at that. The amount of solute in moles divided by the total amount of solute and solvent, also in moles. There's mole percent, moles of solute divided by moles of solution. And then there's the parts. Parts by mass, you're comparing the mass of the solute to the mass of the whole solution. And which part you're getting, there's percent, which is per 100, you multiply by 100. If you want parts per million, then you multiply by a million. If you want parts per billion, you would multiply by a billion. The place I see these the most often, ppms and ppb, is in the water report from the city. They send you all this stuff and it's got all these concentrations, and a lot of them are parts per million and parts per billion. You can also measure parts by volume. This is where you're comparing the volume of the solute to the volume of the solution. And you can do the same thing with the multiplication factors. There are also, you can have mass volume percentages as well. So molarity is the one that chemists like the most because we like moles. Because moles are a counting unit, they relate to the number of particles. And when we do stoichiometry and stuff, we need the number of particles. Everything's related to particles. So the molarity is the amount of solute in moles divided by the volume in liters. Now, we do have a little bit of an issue with molarity and temperature because the volume of a solution will increase at higher temperatures. As you heat water, it gets a little bit bigger. The volume increases a little bit. And since this relates to the volume of the solution, molarity is slightly temperature dependent. And in some situations, that can be an issue. This picture is describing how you would make a 1 molar sodium chloride solution. The balance, of course, doesn't weigh in moles, so you'd have to figure out how many grams 1 mole is. You weigh out 1 mole of sodium chloride. You're going to add water and dissolve it. This is a volumetric flask. I think we used those in the first week, and I don't think we've been back to them. But you're going to put some water in there and slosh it around until it all dissolves. And then you're going to add water until it just gets to the mark on the flask. There's a little mark on the neck, and that would be 1 liter. And then you have 1 mole per liter, or 1 molar sodium chloride solution. Molality is another one. It's not my favorite, but here it is. It's moles of solute per mass of solvent in kilograms. So it's moles per kilogram, but it's solvent. Most of them are measuring the solution. This is measuring just the solvent. So that's kilograms of solvent, not solution. The best thing about molality is it is independent of temperature. The volume doesn't come into it. The mass of the solvent does not change with temperature. The moles of solute don't change with temperature. And so this one is temperature independent. Parts by mass, parts by volume. You're looking at the mass of the solute divided by the mass of the solution. Let's see, where can I throw this in here? No, not like that. sort of a generic description of percent is that it's the part divided by the whole times 100. And if you remember that, you can help yourself out on an exam when you lose your mind and forget what percentages are. So it's the mass of the solute, the thing that you're interested in, divided by the mass of the whole thing. For percent, it's multiplied by 100. So percent by mass. And it can also make a great conversion factor. If you have a concentration in percent, 14% by mass means that you have 14 grams of whatever the solute is per 100 grams of solution. And so if you know the mass of the solution, you can know the mass of the solute that's in it. Parts per million, parts per billion, very similar. So if it says 15 parts per billion, that's 15 grams per billion grams. And you can put whatever mass unit you want in here. You could put kilograms, you could do ounces, you could do metric tons. It doesn't matter as long as the two units are the same. The unit for the solute and for the solution have to be the same. Parts by volume, same pattern. It's just that the solution is made by measuring volumes instead of masses. This is more useful for liquids. So 22% ethanol by volume means that there are 22 milliliters of ethanol in 100 milliliters of solution. That could be slightly different than the mass percentage. So what mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per liter. And that's the size of a 12-ounce can of soda. So what do we do? We're going to have to use the density and the percent mass. Sometimes with a problem like this, you look at it and you're like, yeah, I'm not sure where to start. Well, start just writing stuff down. So 11.5% sucrose. What does that mean? 11.5 grams of sucrose per 100 grams of solution. That looks like it could be a useful conversion factor, right? And then we've got the density over here. The density is 1.04 grams per milliliter. And then this 12 ounces, do you think we need to use that? No, that's just kind of a point of reference. Let's cross that off. So then we've got this 355 milliliters. I approach problems like this using dimensional analysis. So these two both have per units, something per something else, meaning they could be used as conversion factors. Usually that's not what you start with. This just has milliliters, so we're probably going to start with that. So we're going to start with milliliters of solution, and I'm trying to get to grams of sucrose. So then I'm going to look at what I have available. Well, I want to get rid of milliliters, so I could use the density to find grams. That's going to be grams of what? Solution or a solute? Or solvent? It's going to be the solution, right? So I can go to grams of solution. And then this guy relates grams of sucrose to grams of solution. So once I get there, I can go over here. You guys okay with that? So 355 milliliters of solution. It's probably a good idea to label milliliters of what? So then I'm going to have grams of solution per milliliter of solution. So those guys cancel out. And then I'm going to grams of sucrose per grams of solution. So those cancel out. Put all the units in first. This one is 15. I don't know where that came from. 11.5 grams of sucrose per 100 grams of solution. And this other one is going to be 1.04 grams of solution per 1 milliliter of solution. 355 times 1.04 times 11.5 divided by 100. Three sig figs, 42.5 grams of sugar. Any questions? That's not the only way to solve that problem. Some of you learned how to do percentages differently in your math classes, and there are definitely other ways. I like this because it just falls right into the dimensional analysis that we use for so many other things, and so works for me. You should definitely be able to do calculations like this. Mole fraction, mole percent. Mole fraction just gives the moles of solute divided by the total amount of solute and solvent in moles. So it's the amount of solute in moles per the whole solution in moles. Mole percent is just the fraction times 100. So a solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. So molarity. What does molarity equal? It's moles of solute per liter of solution, right? Mole solute per liter solution. Well, what's the volume of the solution? It's 355 milliliters. What's that in liters? 0.355 liters. It's got to be liters. Moles of solute. Well, sucrose is the solute. How many moles do we have? We have to convert. So let's do that up here. This should be old hat. 50.4 grams, and we have to find the molar mass. So we've got 12 carbons times 12.01 plus 22 hydrogens times 1.008 plus 11 oxygens times 16. 342.3. grams per mole of sucrose, which is our solute. Zero 0.14724. It's got 3 sig figs. That's the number of moles. That's not a final answer, so I don't want to round it yet. Always better to carry some extras. You can always round them off later. Moles. So I take that number and divide it by point, that's not a point, 0.355. And now I'll round it off, 3 sig figs, 0.415 moles per liter. Or we sometimes do that as a capital M, 0.415 capital M. Molar, 0.415 molar. The mole fraction. So the mole fraction, we need the moles of solute. We just figured that out, right? So moles, that's going to be 0.14724. And what goes in the denominator? We need the moles of solution. And the only way we can do that is to find the moles of the solute and add them to the moles of the solvent. So down here we're going to have 0.14724 again, and we're going to add moles of water. Well, we've got kilograms of water. So kilograms of water, 0.332 kilograms is 332 grams of water. So I'm going to use the molar mass of water to convert to moles here, and that's 18.02 grams per mole. So 332 divided by 18.02. 18.424. No, moles of water. So I'm going to put that down here, 18.424. You have to be careful on your calculator when you divide by that sum. There's different ways to do it, but you can use parentheses. So 0.14724 divided by open parentheses 0.14724 plus 18.424 close parentheses equals, and the result there is going to be 0.007928. We have to figure out how many significant figures. So the numerator has 3. The denominator, we're not sure, because that's adding. So the 18.424 plus the 0.14724 gives me 18.57124. The uncertainty is largest in this number. It's in the tenths place. So the sum there is 18.5 is the last digit. That's significant. That's also 3 sig figs, and so we can round this to 3 significant figures. So the mole fraction is 0.00793. Is there a unit on that? No, because it's moles divided by moles. I was a little sloppy and I left the moles out of here. But there's no unit on a mole fraction. Just like there's no unit on percent other than percent. Molality. Molality is moles solute per kilogram solvent. So we're going to use the moles of sucrose again. And what's the mass of water in kilograms? Oh, they gave it to us. Almost seems too easy. So we divide by that. 0.14724 divided by 0.332. And this will be 0.443 The abbreviation for molality is a lowercase m. That bothers me because that's also the abbreviation for meters. Or you can say moles per kilogram. Any questions yet? M is just a real popular word when letter. It's not a word. It's a real popular letter when it comes to units. Mole percent. That's just the mole fraction times 100. So all we have to do is take this number that we already calculated and multiply by 100. So that's going to be 0.793%. Now, on a test, do it on your calculator, because I've seen people do some pretty dumb things doing math in their heads. Percent by mass. That's grams of solute divided by grams of solution times 100. What's the mass of the solute? .4. What's the mass of the solution? Well, it's the mass of the solute plus the mass of the solution, right? So I'm going to put that in grams and then times 100. So again, be careful when you're adding down there. So when I add the 50.4 to the 332, I come up with 382.4. The last sig fig is in the ones place, and so I still have 3 significant figures there. And then I'm going to use the inverse button on my calculator, because I like that button, and I'm going to multiply by 50.4. And then multiply by 100. A lot of people forget to multiply by 100. They write it here, and then they don't do it. So this comes out to be 11 point, no, that's 13. I say 11 and I write 13. It's 13.2%. Any questions? This one looks kind of familiar, but it's not the same as that other one that we did. What's the molarity of a 10.5% by mass glucose solution? The density is 1.03 grams per milliliter. Well, I start by asking myself, what's molarity? What do I need to know to find the molarity? Well, molarity is moles solute per liter of solution. Well, I don't have moles of solute. I don't have liters of solution. Let's look at the numbers and see what we do have. 10.5% is 10.5 grams of glucose per 100 grams of solution. And then I also have a density here, which is grams of solution to milliliters of solution. This is one of the unusual times when you actually start with a per unit, but there's nothing else to start with, is there? I'm going to start with the concentration as a percent. So I've got 10.5 grams of glucose. I'm going to write its formula, C6H12O6, per 100 grams of solution. I need to get grams of sucrose to moles of sucrose. That's not hard. I'm going to multiply by moles of sucrose and divide by grams. So that's going to work out. Now I've got the moles on top. I need liters on the bottom. I've got grams. But the density could get me to milliliters, couldn't it? So I could multiply by grams of solution per milliliter of solution. And then the grams are going to cancel out. And then I just need to convert to liters. I'm going to have milliliters on top and liters on the bottom, and milli means 10 to the minus 3. You guys with me? Some of you are sleeping. 1.03 grams per 1 milliliter. And then here I need the molar mass. So 6 times 12.01 plus 12 times 1.008 plus 6 times 16, 180.2. So 10.5 divided by 100 divided by 180.2 times 1.03 divided by 1 EE minus 3 equals 0.600 molar. Any question?